Hey guys, so far we have learned that if you have a function such as this, and we're trying to find the area under the curve from A to B, right? We're trying to find this area. We have learned that this area can be expressed using the notation integral from A to B of f of x dx, assuming that this here function is f of x. And if we called this function y instead, then the same idea would apply. We would just say, oh, this is the integral from a to b of y with dx, right? And so this is called the integral, right? It represents the area under a curve, right? The area between the x-axis and a curve. And we learned how to approximate this area, right? We looked at, dividing it into equal subintervals, and we looked at rectangles, but the one you need to know for this class is trapezoids, right? And you find the area of each of these trapezoids and add them all together, and you have an approximation of that integral. What we've also learned already as well is we've learned about anti-differentiation. And anti-differentiation was the idea that if you're given the derivative, right, like f of x equals f prime of x equals x squared plus 3x plus 2, then you can find the original function, right, which is the opposite of that derivative, right? Like what function do I have to take the derivative of to get here, right? In this case, you get x to the third over 3 plus 3x squared over 2 plus 2x plus c, where c is the constant of integration. And the way that we can check that, this is actually the antiderivative is that we can take the derivative of this function. If we take the derivative of the function, we should get back here, right? So if I take the derivative of this, we get f prime of x. Like right now we're just checking, right? Our solution is up here. We're trying to check. If I take the derivative of this term, I bring down the 3. That's going to give me 3x squared over 3. The 3's cancel. I'm just left with x squared. If I take a derivative of this 2 comes down, cancel this 2, and I'll have 3x, just 3x to the 1, because you subtract 1 and you just get 3x. If I take the derivative of 2x, I get 2, and the derivative of a constant is just 0, so that just goes away and I have 0. And you can see that, yes, this matches this, therefore this is the correct antiderivative of f prime of x. And so we started looking at, okay, well, there's another notation. Instead of saying find the antiderivative, all that stuff, we wrote this other notation which looked like this, and we're finding the antiderivative of f prime of x dx. And you'll notice that this symbol, it was very similar and actually is the exact same thing as this symbol. And the only difference there was that we didn't have these bounds on there, right? We didn't have the a and the b. And so today what we're going to do is we're going to make the connection between anti-differentiation and area under the curve. So we'll just start by reminding you of some notation that we're going to use. We're going to use the capital F as the original function. And if we take the derivative of the capital F, we're just going to get little f. So we're going to use little f as the derivative and big F as the antiderivative, right? So if I take the derivative of big F, I get little f. If I find the antiderivative of little f, I get big F. And then we know that if we take the integral of little f, the antiderivative of little f is, big F plus c, where c is that constant of integration. Okay, so we're going to start with a little simple example that maybe help us frame our thought. We want to find the area under the curve of f of x equals 5. So we're going to just create a real quick sketch here that, it's just going to give us something to look at. Here's f, here's y. We're going to sketch y equals f of x. This is just a constant. Constants are just horizontal lines, right? So the f of x equals 5 just looks like this. And I meant to do that in a different color, so let me just get a different color out. Right, so this is f of x equals 5, and I need to change this. We want to know what's the area under the curve of f equals 5 from maybe x equals 2 to x equals 6, right? So we're going to find the area from 1, 2 to 3, 4, 5, 6. So we're going to try to find this area here, right? And what's kind of interesting about this one is, well, this is just a rectangle, is it not? So I could just use the area of a rectangle, which is going to be base times height. In this case, the base is 4, right? From 2 to 6 is 4. And the height of this is 5, right? Because it's, 5 units above the x-axis. So the area of this one is just 4 times 5, which is 20, right? Now, remember, we also express this area using the integral notation, which would be the the area from 2 to 6 of f of x dx. We know this answer is 20 now, and I could go ahead and write this even further, like area from 2 to, since f of x is 5, I could say the area from 2 to 5 of 5 dx. Now remember, if these numbers aren't here, we know how to do this, right? We know the antiderivative of 5, right? The antiderivative of 5 is 5x, right? So I just want to show you that if we actually find the antiderivative, we get 5x. Now the question is, well, how do I get from 5x to, this situation? And well, it involves something with these numbers. So what we're going to do is we're going to go ahead and keep these numbers over here. We're going to keep our 6 there and our 2 there. And I want you to notice what happens if I plug in the 6, right? We're going to plug in the 6. That's going to give me 30, right? So let's think about graphically. What is the area? What is that saying? What is that 30 telling me? Well, that's telling me the area from 0 to 6. So that's 30, right? If I go from 0 to 6, that's 30. And then if we plug in the 2, we're getting 5 times 2. Right, we're plugging in this 2. We're getting 5 times 2. That's 10. And if maybe you notice, that's the area from here to here, right? So this area, let me clean this up a little bit. This area here is 10. The area from there to there is 30. How can we get our actual answer of 20? Well, we can subtract 30 minus 10, right? The whole area minus this piece here that we don't want. And so we could subtract these to get our actual area of 20. And so let's think about what we did, right? We found the antiderivative of this, which was 5x. We plugged in the 6, right? We plugged in the top one. We plugged in the bottom one, and we subtracted top minus bottom, right? So let's see if that still applies to in other cases. Okay, so we're going to look at another example. We want to find the area under the curve of y equals 2x from x equals 1 to x equals 6. So we're going to start by sketching a graph, right? So we're going to call this, y equals 2x, and we're just, generally sketching it. And we want to figure out, okay, what is the area under this curve? Well, we could do this just geometrically, right? We could look at this like such and be like, hey, this is a triangle, right? Triangle has area, it's not quite a triangle, but it's close to a triangle. A triangle, basically, it's this big triangle minus this little triangle here, right? I could do the big triangle minus the little triangle. Okay, so let's start by finding the area of the big triangle. The area of the big triangle is base times height over 2. The base of this is 6. The height is 12, right? At x value is 6, the y value is 12. And so the area of this would be, the area of this triangle would be 6 times 12 over 2, right? 1/2 base times height. But then we need to subtract this little triangle over here. So minus the base of this little triangle is 1. The height of that little triangle is 2 over 2. And that's going to give us 36 minus 1, which is 35. So our area is 35. Now remember, the area under the curve between 2 points, we said the notation we were using was the integral from 1 to 6 of our function with respect to x, right? And we know how to find the antiderivative of this. The antiderivative of this is you add 1 to the exponent, so that's going to give me x squared, and we divide by whatever we get over 2. Don't forget that this 2 is there as well, right? So these 2's are going to cancel. So our antiderivative is just x squared. Now remember, we want to hold on to these side bounds here, right? So we're gonna go ahead and put those over here, 6 and 1. Remember what we did last time, right? Last time we went ahead and plugged these in, right? If I plug in 6, I get 6 squared. We're going to plug in 1, we get 1 squared. Remember last time we subtracted, so we're going to go ahead and subtract again. And here we're going to get 36 minus 1, which is 35, right? And you can see that it does give you the same area as you would if you'd use a geometric formula. And this is actually true for any function whatsoever, right? So let's call this, let's just draw a graph here. Let's say this is my function f of x, right? Notice the little f. And let's say we go from a to b, right? So we're trying to find this area. Then based on what we were just talking about, this area we've been representing as this integral from a to b of f of x dx. Think about what we just did. What did we do? Well, we integrated this. We found the antiderivative. Remember, according to this notation, we're going to use big F as the antiderivative. So we're going to say, okay, this was big F of x, right? And we kept these things b to a, and then we plugged in the b and we plugged in the a, right? And so that would give us big F of b minus big F of a, which is, this is the antiderivative evaluated at b and the antiderivative evaluated at a. And that actually tells us the exact area under this curve, right? So that, what we just showed, is called the fundamental theorem of calculus. So, and here it is written out nicely for you. It has to be a continuous function. You're not gonna have to worry about non-continuous in this course, but you know, if you had gaps and stuff, it wouldn't work. It's just saying if I basically the integral from a to b of f of x dx is just simply the antiderivative evaluated at b minus the antiderivative evaluated at a. So let's look at some examples. Okay, so we'll do these two examples, and we should also talk about something else, right? So notice we're being asked to integrate from 1 to 2 this function here. Again, graphically what this means is, you know, if I graphed this function x to the third minus 4x plus 5, maybe I get something like this. We're going from 1 to 2, so what we're doing is we're finding this area under the curve of this function from 1 to 2, right? And what we know is that the area under this curve will simply be f of 2 in this case minus f of 1, right? Where f is the antiderivative of this. If this function is f of x, we're finding the antiderivative, right? So we're going to start by finding the antiderivative. Antiderivative is just what function did I have to differentiate to get to here? So the rule is basically add 1 divided by whatever you get to the exponent, right? So it's x to the 4th over 4 minus, this is a 1, add 1, you get 2, so minus 4x squared over 2. And then this is just going to be 5x. And then if you remember, hopefully you noticed in the previous ones and you asked, like, what about that c that we get? So today, now we'll actually go and consider that c, right? And then we'll go ahead and hold on to these 2 and 1, right? And that's where this comes from. We plug in 2, we subtract the 1, right? So we're going to go through and we're going to plug in the 2. So we're going to get 2 to the 4th over 4 minus 4 times 2 squared over 2 plus 5 times 2 plus c, right? That's what we get in that's what we get when we plug in 2, and then we're going to subtract whatever we get when we plug in 1, right? Now we're plugging in this 1 everywhere, so we get 1 to the 4th over 4 minus 4 1 squared over 2 plus 5 times 1 plus c, right? And then we go in and simplify all this stuff. 2 to the 4th is 16 over 4 is 4. 2 squared is 4. These actually just cancel, make 2. So 4 times 2 is negative 8. This is 10. This is c. We're going to put a minus sign there. Where this is 1/4. This is, these cancel, you get 2 plus 5 plus c. Go ahead and do some more work here. 4 minus 8 is negative 4 plus 10 is 6. So we have 6 plus c. Minus negative 2 plus 5 is 3. 3 plus 1/4 is 3 1/4, so that's like 3.25 plus c, right? Keep these parentheses because you know you have to distribute the negative in there. And what I want you to notice is what's going to happen to my c? Well, it's going to cancel out, right? Because you have a positive c and a negative c. And so we're left with 6 minus 3.25, which is 2.75, right? So that's how you evaluate that integral, and that would actually be that area that's under that curve. And this thing that happened with c will always happen with definite integrals because you're always doing, you know, this one minus this one, and those c's will always cancel. So typically when we're doing definite integrals that have these numbers on them, we don't need to deal with the c. We don't need to even write it down. Okay, so as you can see, like the math in here gets a little bit complicated with a bunch of fractions and, you know, order of operations and all that junk. One way to check your answer is to use your calculator, and I'll show you how to integrate on your calculator for definite integrals. So you're going to press math. You're going to go up or down until you get to this fn int, that's function integration, right? It's right below the derivative. So we're going to put that on there, and we're just going to put in our numbers, right? 1, 2, we put our function here, which is going to be x to the third minus 4x plus 5. Here you got to put dx and enter, and you can see 2.75, which is the same thing that we got here. Okay, so real quick, we're going to come back to this problem that we did on Thursday last week, and we used trapezoids to estimate the area under this curve from there to there. And what we ended up getting in this case was 43. And remember, 43 was an approximation of the area. And then we also found the cubic regression curve. And let me get that again. Okay, so we can get that by putting all those data points into this here list, and then going just press stat, go over to calculate. It said it was a cubic function, so we go down to number 6, and we tell it to find this for us. And when we do that, it gives us our A, B, C, and D value, right, which I have written our equation down here with those values. We could then put that value into our equation up here, right, into y equals, and we could create a graph if we wanted to. The graph's going to look something like this. I probably need to edit the window here. Okay, we can just change the window to be the same as this, this grid in here. Press graph, and it looks like this, which is pretty much the same as this, right? And I'll show you another way to find the area under the curve. We can do second trace. You see in number 7, you have the little integral sign, so we're going to press 7. It says lower limit. We're going to put in the lower limit of 0. It's going to say upper limit. The upper limit in this case was 10. Press enter. And what it's going to do is actually going to shade it for you. And it's going to find the area. And it turns out the area is 42.6, right? So the better approximation of the area is 42.6. This is probably very, very close. Again, the calculator is going to round a little bit, but you can see our approximation was pretty close to the exact answer that integral gives us.